In this video, I'll be talking about modeling the deterioration of infrastructures over time. My name is Zachary Amida, and the work I'm about to present has been published under the title Network Scale Deterioration Modeling of Bridges based on Visual Inspections and Structural Attributes. So the presentation is going to be organized as follows. First, we're going to have a look at the context and objectives, and by this we mean exploring some of the characteristics of the database that we are working with and our objectives in working with it. After that, we're going to review an existing approach for modeling the deterioration based on visual inspection data, which is the state space model or the SSM model. So we're going to have a look at some of the characteristics of this approach, and then we will move on in the following section to talk about the proposed model or the SSM-KR model, which would allow modeling the deterioration based on not only visual inspection data, but also the structural attributes of the bridges or the infrastructure that we have. Finally, in the last section, we're going to talk about we're going to show some of the deterioration analysis and results that and the improvement that we've gained after factoring structural attributes, whether it's with synthetic data or real data. So first, let's start with the definitions. Visual inspections, what is it? Visual inspections is a monitoring technique that is where an inspector would evaluate the health state of a structural element and then would report its condition at a given time. This technique can be applied on a network scale, and by a network here, we are referring to a set of bridges. So in our case, we have around 10,000 bridges which exist within the province of Quebec. So all these bridges are within a certain region. Now, some of these bridges are similar to each other in terms of material, traffic, or location, and while others are completely different. Now, in order to understand how visual inspections are performed on bridges, we need to know what's within each bridge. So, according to the Manual of Inspections from MTQ, each bridge is composed mainly of two types of elements. The first type is the elements that relates directly to the structural safety of the bridge, such as the beams and slabs and so on. And the second type of structural elements are elements that relates directly to the serviceability of the bridge, such as the barriers and the pavements elements. Now, each one of these categories is composed of a number of elements. So there could be 3 slabs within a bridge and 20 beams and so on for each one of these categories. Now, visual inspections are performed directly on the structural elements. So at a given year, let's say 2008 for this particular bridge, the visual inspections are performed on the structural elements of this bridge. And visual inspections in general, they are performed on a yearly interval. So it could be every 1 year or 2 years or up to once every 4 years. In this case, we have every 3 years, we have another round of inspections, and it carries on for all structural elements. Now, the focus of this research work is really at the structural element level, as we're going to see later. So let's have a look at an example for visual inspection data on a structural element. So in this example, we see this graph. On the x-axis, we have the timeline on a yearly scale. And on the y-axis, we have the health condition of a structural element, ranging from 25 for the worst possible condition up to 100 for the best possible condition. Now, the inspection data are reported by the blue points, and each point is associated with an inspector, represented by the letter I and the ID number, as you'd see. So a different ID number means it's a different inspector. Now, one thing you can notice from this example is that first, the data is very limited as a time series data. It's really limited. We have 4 observations only over time. The other thing is that there's the visual inspections in general are subjective by means that they rely on in a large part, they rely on the judgment of the inspector. So that's why we can see high variability in the data, as you'd see here, why we are expecting you see a deterioration curve from the best condition to the lowest condition, we can see that there is a variability in the data that we have because we have different inspectors over time in part. So this is one example. However, there are thousands of other structural elements that they could have a better data or worse data. But this is like really the average case overall. So our objectives in working with this data is really to model the deterioration behavior based on the data from the network of bridges collectively. So, and that would really include integrating the structural attributes in the analysis. So we don't want to only rely on the visual inspection data, but we want to bring in the characteristics that define each bridge. The other thing is that we aim to estimate the deterioration rate over time for each one of these structural components. So in order to do so, first let's have a look at an existing approach that would allow modeling the deterioration based on visual inspection data. So this approach really relies on describing the deterioration by a kinematic model, where we have the kinematic equations for the condition, the speed, and acceleration. These kinematic equations can be represented by the matrix form, as you would see here, where I have xt is the state at time t, and the matrix A, xt minus 1, and wt. Now, the method that would allow us to employ such an approach to the kinematic model is really the state space models. State space models is composed of two types of models. The first model is really the transition model, which is described by xt equals to a xt minus 1 plus wt, which is exactly the kinematic model that you see above, where a is the transition matrix and xt minus 1 is the state at t minus 1. Wt is the process error, described by a zero mean and equivariance matrix qt in this case. So the role of the transition model is really to give me a prediction over time given a state at time t. So let's see. For example, if you look at the lit graph in the lower corner, you can see on the x-axis the condition, the y-axis the time, and let's say that we have a state at time t0. So using this transition model, I can do a prediction at the state time t1. Now, if I have an observation at time t1, then I want to update my model prediction with the information of this observation. And in order to do so, I would need to have an observation model that would characterize this observation. So this observation model is described by yt, which is the observation at time t, equals to c, the observation matrix, multiplied by xt, the state at time t, plus vt, which is the observation error. Now the observation error is described by zero mean and the variance sigma v squared. So using this observation model, I can update the state with the observation, and you see, like I would get the red dot on the graph. And I can carry on in the same way. So like at this time t1, then I can do a prediction using the transition model. And if I have an observation, I can again update my model prediction with this new observation. So employing these methods, the prediction and the update steps can be performed using an algorithm called the Kalman filter algorithm. Now, some of the special characteristics about visual inspections, as we mentioned earlier, is that we have different inspectors over time, and the evaluation is really subjective. So if we can employ this particular observation model, it means that we can assume all the inspectors have the same performance over time, which is not true, again, because this visual inspection, like the observation that we have from visual inspection, is really subjective. So that's why it was considered that we have an observation error for each inspector. This observation error is estimated based on the entire data set collectively, so it kind of evaluate the performance of the inspector over time. And the other characteristics of visual inspections is that Within the SSM model that's utilized for modeling the deterioration based on visual inspections, we have a space transformation, which would allow the uncertainty to be dependent on the state. And another thing, the space transformation would allow bounding the condition estimates, the deterioration condition estimates within the feasible bounds. So as you say earlier, we have the observations ranging from 25 to 100, so that we need some way to bound this estimate. So this is really using the transformation function G. The other thing about this SSM model is that it's a model for modeling the deterioration behavior. So the curve that we would expect is monotonic. And that's why the deterioration speed has to be within the negative domain in this case, because our condition is ranging from 25 for the perfect up to down to 100 for the worst condition. So we have a constraint that would ensure the monotonicity. Now, these characteristics are discussed in the details of in the work of Amida and Golay in 2020. Now, this is the general view of the SSM approach. Now, however, this approach has some limitations. These limitations are really, first, that this approach relies only on visual inspection data, so it doesn't take into account like some of the characteristics of the bridges. And the other thing is that estimating the deterioration speed in general, and this approach is really challenging. This is because the deterioration speed is not directly observed, so we don't have any observations for the speed. And the other thing is that the number of observations on the condition is limited. As you saw, we have 4 observations per time series, or 3, or in some cases there are 2. So this is very limited number for to rely on for estimating the deterioration speed. So the idea here is that can we include the structural attributes in the analysis, and can we exploit because we have thousands of structures, can we exploit the similarities between these structures by including the structural attributes and by relying on a regression approach? So in order to illustrate this idea, let's have a look at an example that would demonstrate that. So imagine you have a bridge, and shown in this picture with the ID 023, and this bridge has been inspected 6 times over time. Now, my estimate based on this number of inspections, my estimate for the deterioration speed would be relatively reliable. So I would have a low uncertainty around my estimate for the deterioration speed, and it will be closer to 0, given that this is a new bridge. Now, if I have another bridge, in this case 002, and this bridge has been inspected 5 times over time, my estimate for the speed also would be relatively with low uncertainty, because again I have a relatively enough number of observations. Now, if I take another case for the bridge 015, this bridge has been inspected 2 times, so my estimate for the deterioration speed would have really large uncertainty around it. And the idea here is that, can I use the structural similarity in order to update my deterioration speed estimate such that I can have a more reliable estimate? In this case, like we can see that bridge 015 is probably more similar to bridge 002. That's why like my estimate for the deterioration speed might shift in that direction. And by leveraging this information, I would have a lower uncertainty around my estimate for the deterioration speed. So the idea is really to rely on the structural similarity, and the method that would allow us to rely on that similarity is really the KR approach, or kernel regression. So that's why the name of the model is SSM-KR, which combines the state space models with the kernel regression. Now, the structural attributes could be like the location. So bridges in the south and north of the province are more similar to bridges compared to bridges in the north, and they can go under like also similar environmental factors. And also there's the age, so old bridges versus new bridges. Also, there's the material, so wood versus steel. And finally, the condition, so bridges that are that have a low condition, they have a different deterioration speed than bridges or structural elements that are new or in a better condition. So these are like general structural attributes that can be considered. There could be others. And now, in order to illustrate the formulation of the SSM-KR model, is that imagine you have two structural attributes, and the structural attribute Z1 and the structural attribute Z2. And imagine in this case that you know the true response for the deterioration speed, so which is represented by this curve that we see on the vertical axis. Now, the idea here is that in order to model this curve, we need observations. However, again, the deterioration speed, we don't have any observations. But what we have the structural attributes associated with each structural element, and we also have the estimates for the initial estimates that are based on the SSM model. So using the SSM model, I would have an estimate for the deterioration speed in terms of the expected value and the uncertainty. So the idea is that can we leverage these information, the structural attributes and the initial estimates from the SSM model, in order to model this surface that we have for the true response. So the way that we've done it is that we propose discretizing the horizontal plane that we have. So we've discretized it into something we call the reference points, a set of reference points. And these reference points, they have the coordinates ZC1, ZC2, which are fixed coordinates, so they don't change. However, the third coordinate, which is on the vertical axis, it's a random variable. And we represent it by mu.z and sigma.z in terms of random variable. So this random variable, we can start with any initial value for this random variable and a large uncertainty. And then what we're going to do is really recursively updating this random variable mu.z and sigma.z based on the information or the estimates of the SSM model. So we do a recursive update, we update these states, and then these states we can rely on them to update our estimates in the SSM model, and so on. So this recursive approach is explained in further details in the work in the paper that has been published. So in order to have an overview of the SSM-KR model, let's look at this flowchart. So for any bridge within the network of bridges, and for any structural elements within this bridge, we have the observations for this structural elements, which are the inspection data. And we also have the structural attributes associated with this structural element or with this bridge. And from the structural attributes, we can get the initial estimate for the deterioration speed. And for the observations, what we do is that we pass them into the transformation function, G, to get the observations in the transform space, which are from -infinity to +infinity. So having the initial speed estimate and the observations in the transform space, we pass them into the Kalman filter that we have here. The Kalman filter would provide me with the prediction and the update steps, would perform these. And at each time step, I need to ensure that my deterioration speed is negative. In case if it is not, then I apply the PDF truncation method that we have. And this check we would perform on each time step. The Kalman filter also would provide me with the log likelihood, which would help me in estimating the model parameters. Now, after the Kalman filter, we move to the Kalman smoother, which is the same thing. So we check for the condition on the deterioration speed at each time step. From the Kalman smoother, I get my model estimates, but these model estimates are in the transform space. So I do a back transformation to get my model estimates in the constrained or bounded original space, which would which would be helpful more for the interpretation process. So this is like the general idea of the framework. Now there are definitely more examples and more explanation about this framework in the paper that we have. So let's look at so in order to verify the performance of this proposed framework, what we've done is that we've generated synthetic data, and the way that we've generated synthetic data here, I'm gonna like provide really general overview on the method. However, there are definitely further details in the paper. So the way that we've generated that is that, imagine like if we have this time, so in this graph we have on the x-axis is the timeline on a yearly scale, on the y-axis is the condition, and imagine you have the true curve of deterioration. Now the idea is that what we would do is that we would assign inspectors at different time steps. So these inspectors, they are synthetic, and by synthetic it means that we know their standard deviation of their error, their standard deviation, and their error characteristics, basically. So based on these, what we do is we assign the inspectors, and then we take a sample from each error distribution that we have for each inspector. So this sample is really represent the the observations or the inspection data. So what we do after taking the sample is that we hide the inspectors' true standard deviations, we hide the true deterioration curve, and we will end up only with the inspector ID and the inspection data represented by the blue points. So it's really similar to the real case. And we store this into the synthetic database that we have. So, and we do this like based on the same method, we generate thousands of structural elements that would allow us to verify our model performance. So let's look at an example of the synthetic data. In this graph, we have two figures. So the figure on the left is for the condition, and the figure on the right is for the speed. Both x-axes represent the timeline, same time steps, and on the y-axis here, on the graph on the left, for the condition, we have the observations are represented by the blue points, with each observation associated with an inspector, as shown, and we have in this case different inspectors over time. While for the speed, we don't have any observations. So the uncertainty for each inspector is shown on the inspection data as estimated by the vertical lines, as we see here, where we have the blue vertical line represents the estimated inspector uncertainty versus the black vertical line shows the true inspector uncertainty in this case. So if we show the model estimate, which is represented by the red dashed line, and the uncertainty around it with the 2 standard deviation and 1 standard deviation for the darker region around the model estimate. Now this is for the condition on the left and for the speed on the right. And if we're gonna show the true deterioration curve, so for the condition it's represented by the black dashed line. As you'd see in this case, that given the low number of observations, the true condition is still within the confidence interval of our model, and the performance is acceptable given the low number of observations and the high uncertainty around each one of these observations. Similarly, if we look at the deterioration speed, we see that our estimate for the deterioration speed is really good given the true deterioration speed represented by the black dashed line. Now, because we have the SSM-KR model, let's look at the SSM model on the same graph. So the estimate for the SSM model is shown by the black dashed line with the square points. So for the condition, you see initially we have a similar performance, but however over time it started to diverge. However, for the speed, you'd start to realize that the difference is really in the initial speed, where like the initial speed for the SSM model was closer to 0, and farther from the true deterioration speed, you see that the SSM-KR model has a better initial estimate overall than the SSM model. So This is for one structure element. Now let's see the overall performance for a bunch of structure elements, so a bunch of beams that we have. So in this assessment, we are looking at the bias and estimating the initial deterioration speed, and this is synthetic data. So we know the true initial speed. So here we have a histogram where the histogram represents really the error, which is the difference between the initial deterioration speed minus the estimated deterioration speed based on the SSM model. Now, as you'd see, because the histogram is far from zero, then this tells us that there is a bias in the model estimate overall for the initial deterioration speed. Now, if we look at the SSM-KR model, the same histogram, same everything. However, here we factored structural attributes. We can see, based on the SSM-KR model, we can see that this histogram is centered nearly around zero, which means that there's like very little or negligible bias in the overall estimate for the deterioration speed. So this is for the part for synthetic data. There are further examples that show step-by-step how the SSM-KR model works. But now let's move to the real data. So in this case, I'm going to show an example for a time series. Again, same thing. The condition is on the left and the speed on the right in terms of graphs. The timeline is on the x-axis, and the vertical lines for the left graph is for the condition. And you see with the observations represented by the blue points, with each observation associated with an inspector, represented by the letter I. So in this case, and again, the speed, we don't have any observations. So if we want to show the inspector's uncertainty as estimated by our model parameter estimation framework, you see it represented by the blue vertical lines. And the model estimate is represented by the red dashed line, and this is based on the SSM-KR model. Now, and we have also the confidence interval around our model estimates. Now, this for the condition and also for the speed on the right. Now, here, it's a real case. We don't have access to the true deterioration curve. However, here, since we are comparing our SSM-KR model versus the SSM model only, we can plot the SSM model performance. And as you'd see, that the SSM-KR model shows a better adaptation for the observation data. This is because we have a better estimate for the initial speed. So we have, or it shows a more resilient transition throughout the time, over time for the deterioration speed for the SSM-KR compared to the SSM model as we see on the right graph. Now this is for one case of structural element in the real case. Now let's have a look at another case. Also, again, here we have kind of a jump over time between 2011 and 2015. So this is for, again, the condition on the left and the speed on the right. The x-axis is the timeline. And if we plot the vertical lines, the uncertainty for each inspector represented by the blue vertical lines, and we have the model estimate is shown by the red dashed line at the confidence interval for the condition and for the speed. And again, if we want to see the SSM model performance, we see that again, in this case also, if we look at the condition, we see the SSM-KR shows a better adaptation to the data to the observation data. And if we look on the graph for the speed, it shows a more realistic estimate for the deterioration speed, starting from an initial estimate that is more consistent throughout the time series compared to the SSM model. So these are like really individual cases. Now, if we want to examine a bunch of cases for real data for the beam structural elements, so again, we have like around 10,000 structures, and what we've done is that we've taken a subset of bridges. So this subset of bridges, they have beam structural elements. So we've taken all these subset of bridges. We called it the test set. So we've never used it in training the model parameters or estimating any hyperparameters in the KR model or in the SSM-KR model in general. So we've taken this test set, and what we've done is that we've evaluated the performance of the SSM-KR versus the SSM model. So, and the measure for this, we've used the log likelihood. So the log likelihood for the SSM model is shown to be minus 8822, while the log likelihood for the SSM-KR model is minus 8482. And in general, the higher the log likelihood, the better it is. And this is on the test set. So that would show that overall, the SSM-KR model has better performance in the real case also. So it coincides with the results of the synthetic database. So this is like really the analysis for the real database. However, there are like other analyses that are available in the paper, which and there are further explanation about like all the details in each example. Now, as for the conclusion, in this research project, what we've done is that we've developed a network scale deterioration model that allow modeling the deterioration based on visual inspections and structural attributes of bridges of our infrastructure. This approach, factoring structural attributes, allowed improving the estimation for the deterioration speed by compensating for the lack of data for some of the bridges. So for bridges that has a lower number of inspections, we rely on the structural similarities with other bridges that have more data, and which would provide us with better estimate for the initial deterioration speed, which compensate again for the lack of observations or inspections. And the other thing is that it allowed reducing the overall estimation bias, as shown in the synthetic experiment that we've conducted. The predictive capacity of the proposed new framework or the SSM-KR model have been verified and validated using synthetic and real databases. As for other details and other conclusions, they can be found in the paper, which is available in the link below. Thank you for listening.